Hey everybody! I thought what we would do today is look at this quiz problem that I gave this week. And I gave this one in solid mechanics because we had to review centroids and moment of inertia. So let's go over this one. And this is from some version of the Hibbeler statics book. I don't remember which version, but that's where I got it from. So we want to determine the distance y bar to the centroid of the beam's cross-sectional area. So we can see y bar is right here. C denotes the centroid. All right. And then after we do that, we want to determine the moment of inertia about the x prime axis. Well, here is the x prime axis. So the x prime axis is a centroidal axis because it goes through the centroid, right? So let's go ahead and walk through the steps to do this. Now, I told my class to use this x-axis here as the reference line. That way everybody would have the same measurements. So that's what we'll be using when we go through this problem. All right, now this is a problem where we're going to use composite bodies because obviously we can separate this thing up into multiple simple geometric shapes. So I'm going to find the centroid first, that y bar value. So we want to find that height above the x-axis. And then once we have that, we can find the moment of inertia about this x prime axis here. All right, so I'm going to make a table. That's what I always do for centroids and moments of inertia. So we got region, we're going to have area, which is A, y tilde, and then we're going to have y tilde times A. All right, so let's go through and I want to pull off the easy shapes here. So I'm going to say this one right here is shape 1. And we're going to make it be that right there. So it's going to be 25 this way. And then if we look over here, it's 100 in that vertical distance. So let's write that down here. So we got 25 and then 100. And then let's do this one over here. So this will be region 2. So same dimensions here on this one. All right, so 25, 100. And then let's jump down here. I'm going to do this one. So that'll be region 3. And then finally, I did this one right here. So this one would be 4. Okay, now this length, notice this one, we got the space here, so you have to include that 25. All right, and some people on the quiz did not include that. So we're going to have 50 plus 25 plus 75 plus 25 plus 75 plus 25 plus 50. All right, so that's going to give us 325. And then this height here is giving us 25. Okay, so now we have our regions. And I think those would be the easiest ones to use. Some of my students put more regions than this, but I think those 4 are probably the easiest ones. So now what we're going to do, we're going to fill out this table as we go through each region. So A is just the area. All right, so obviously area of a rectangle, you're just going to do 25 times 100. So that gives us 2500. Now what's the y tilde? Do you remember? Well, remember the y tilde is basically going to be the measurement to the centroid of each individual region. Okay, so this one right here is going to have a centroid location right there in the middle. So if we put it over here, let's just put it right there. And we want to measure that from our reference line. Okay, so I said the reference line was this x-axis. So that means I want to find the distance from here up to there. Okay, so that's going to be that y tilde for region 1. Now let's see what that would be. So I've got to go up 25 just to get across this region 4 here. So go up 25 and then we want to go to the midpoint of this rectangle. So the length was 100. So that means this distance from the bottom of the rectangle up is going to be 50. So we're going to have 25 plus 50, which is obviously 75. Now we just multiply these two numbers together. And what does that give us? Let's see, 187,500. So that's our first region. So now we go to the next one. So this next one is essentially going to be the same thing because we're just looking for vertical distances. So again, C would be right here in the center. So the y tilde would be from here to here, just like before. So that distance is going to be the same there. All right, so we're going to have 2,500 for the area from 25 times 100. Y tilde, again, we go up the 25 and then add 50 to get to that midpoint. So that's going to equal 75. And then here you get the same thing that we had above. So the 187 and then 500. All right, now let's go down here to this one. So area, same thing, 25 times 100, which is obviously 2,500. And then y tilde on this one, I'm going down here, right? Now I want to measure from the same reference line that I did with these two. So I'm going to start here and I'm going to go down that way. So now what would that be? Remember, this is 100. So that's going to be negative 50, right? Because I'm below the reference line. So anytime we go below that reference line, we're going to make it negative. When we go above, we're going to make it positive. So this will be negative 50. And then we multiply. So on this one, you're going to get negative 125,000. And then finally, we get to this one. All right, so area is different here. We got 25 times 325. That's going to be 8,125. Y tilde here. Find the centroid of that rectangle. So it's going to be like right there in the center. Like right there. So we need to go from the x-axis up to that point there. Kind of hard to show in that little picture. But that's going to be that midpoint. So the height here was 25, so I'm going to go halfway up. So it's going to be 25 over 2, which is 12.5. So now here we do 12.5 times 8125. And that is 10,000, well, let's see, not 10,000, it's 101,563. All right, so now we're done with the hard part for this one. Now remember, our equation for y bar is going to be the sum of y tilde a over the sum of a. And we can get these values here from the table. So let's sum up this last column. That'll give us the numerator. And then if we sum up the area column, we get the denominator. All right, so the sum here is going to be 351,563. And then the sum of the area is going to be 15,625. And then we just plug those into this equation. And your result will be 22.5 millimeters. All right, so that's how high up C is from this x-axis. All right, 22.5. So that's the first part. Now we got to find the moment of inertia about the x prime axis. And we're going to use some of this information from this table. All right, I'm going to make a new table for the moment of inertia one, but we will copy down some of that same information. Okay, so I'm going to have region again. I'm going to have area. I'm going to have dy. We're going to have a dy squared. I bar. And since I have room, I'm going to go ahead and put I bar plus a dy squared. All right, so remember this equation right here, this is that parallel axis theorem. Okay, so we're basically just going to get our components as we go through the region and add them all together and then get this. Okay, so let's go through each region. So we're going to use the same regions we had before, so 1 through 4. And you can write all these down again, whoops. Or you could just put 1, 2, 3, 4, same thing. All right, I'm going to run out of room here. Okay, so now we've got that. And let's go ahead and copy down the area values because the areas aren't going to change. So I've got the 2,500 for the top 3. And then we're going to have the 8,125 for this bottom one. Okay. Now dy, this is the part usually that messes people up when they first look at this. So let's think about what this is doing, the parallel axis theorem. Remember when we're doing parallel axis theorem, we want to find the moment of inertia about an axis that's not through the centroid. Right, that's what we're looking for. And I'm talking about when we're doing each of these regions here, not the whole piece here. So if we think about it that way, then let's draw some axes. So the dy, we're going to get that by drawing the centroidal axis for each region, right? So let's just call that x1. And we want the moment of inertia about x prime. So dy then is going to be that distance right there, okay? Because this is the centroidal axis, that's where we're getting this I bar column. So we're going to find the moment of inertia about the axis here through the centroid in region 1, and then to adjust for the fact that we want to take it about this x prime axis, which is shifted downward from the C of the region, we need to do parallel axis theorem. So we're going to do the A times dy squared, right? So that takes care of the fact that the centroidal axes don't line up in this problem. So that's what dy will be. All right, it's just the difference in location between those two axes. And we're doing a vertical distance because we want to take the moment about a horizontal axis. All right, so that distance has got to be in that y direction. Now, there's an easy way to calculate this. If you look at our calculation here, we had y prime, or not y prime, y tilde. It went all the way up to c, right? We had that value. And then we've got y bar, which we calculated here. So if you look at this dy, you'll notice that that is the same thing as the difference between y tilde and y bar. Okay, so we want to take the difference between these two values. We're going to square it over here, so it doesn't really matter if it's positive or negative. We just need to find that difference. Okay, so that's what we're going to do. So let's just put absolute value of y bar minus y tilde. Okay, so with that, for the first one, y tilde was 75, and then y bar is 22.5. All right, so if I subtract those, it's going to give me this distance right here, that little tiny dy distance. So that's what we want for this first entry. All right, so just subtract that, find the difference. It's going to be 52.5. Okay, well, we're going to get the same thing for this region too, because it's basically at the same location, right? So now I've got a centroidal axis right here. I want this distance there. All right, so that's our dy. So now we just take the difference between the y tilde and the y bar, which takes us up to that x prime axis. Okay. So 75 minus 22.5, and then that's going to be the same thing we had before. So 52.5. Okay, and we'll get to these parts in just a second. Let's go ahead and fill these in so I don't have to go back up and down once we get done. All right, so next one is region 3. So region 3 is this bottom one here. So let's draw our axis. So we've got the x-axis here that goes to the centroid of region 3, and I want to find the distance between this x prime axis and this one. So now we're going to have that distance. All right. So we're measuring between x prime and then this centroidal axis here. That's going to be my dy. Okay. Now this one's a little bit different, right? Because we're dropping down below that reference line. So remember I said if we go below the reference line, it's got to be negative. So for this one, essentially we're going to have the y bar value, which is 22.5, plus the distance from the reference line down to the centroid, which is 50. Okay, but you can use the same kind of equation. We'll just have 22.5 minus negative 50. So then those become positive. And then that gives us 72.5. All right. And then last one, this drawing's getting a little busy here. So we've got this horizontal region. So again, we'd want to draw a horizontal line through the centroid there. And now I want to find the distance between this line and this line up here. All right, so this distance right here would be the dy for the horizontal region. Okay, so that value is going to be 22.5 minus 12.5, which is 10. All right, so now we're done with the hard part. So let's go ahead and do a times dy squared. So we're going to square this number that we just got in this column here. So that, like I said, that's why it doesn't matter if it's positive or negative. People always ask that, and it doesn't matter because you're going to square it anyways. So we're going to do 2,500 times 52.5 squared. And that's going to equal 6.891 times 10 to the 6th. You're going to get the same thing for this second region because you have the same values. So we can just write that back down. For this one, it's going to be a little bit bigger because we have 2,500 times 72.5. So this one will be 1.314 times 10 to the 7th. And then finally on this last one, 8,125 times 10 squared. So 812,500. We'll finish that column out. Okay, so now we've got this done. We've got 2 more columns to do. All right, now I bar, this comes from a centroid table, which hopefully you have one handy. Okay, so if you look at the one from the Hibbeler book, this is what it looks like. So we've got this rectangular area. I want to find the Ix equation because I'm looking for the horizontal axis. So we're going to do 1 over 12 times base height cubed. Okay, so that's what we'll use for this one. And we're going to use the same equation for all 4 because they're all rectangles. All right, so for this one, just to show you how to do it, the base would be 25, height is going to be 100. So we're going to have 1 over 12 times 25 times 100 cubed. And that's going to give us 2.083 times 10 to the 6th. All right, and that's going to be the same thing for this one here. We're kind of getting off here on the spacing. All right, so this one goes together and this one goes together. For this one, we got 25 and 100 again, right? So you're still going to get the same 2.083 times 10 to the 6th. And then finally this last one. This one will be 1 over 12, base is 325, and then height is 25. So cube that. And that gives us 423,177. Okay, so now we're left with this last column. So this is the easy part. All we're going to do is add these two numbers up from the previous columns. Okay, so for this one, we're going to have 2.083 times 10 to the 6th plus the 6.891 times 10 to the 6th. And that's going to give us 8.973 times 10 to the 6th. You probably guessed we get the same thing in the second row since the numbers are unchanged. For this one, it's going to be a little bit different because I have 2.083 times 10 to the 6th plus the 1.314 times 10 to the 7th. So this one ends up being 1.5224 times 10 to the 7th. And then finally the last one, just add these two values up. You're going to get 1.236 times 10 to the 6th. Now I want to sum this column up because remember for the parallel axis theorem, if we have multiple regions, you want to do the summation of these calculations for each of the regions. So let's add these up. And that gives us 3.44 times 10 to the 7th millimeters to the 4th. So that would be Ix prime. All right. And remember, the moment of inertia, what that does is it gives you basically an indication of how the beam or the object will resist bending. Okay, that's what we use it for in mechanics and materials. So the larger this number is, the more resistant it is to bending. Okay. So hopefully y'all found that one helpful, and I will see y'all next time for another example.